Welcome to Lecture 3, Part 3, Solution Results Using Gauss-Jordan. Real quickly, we are able to reduce, let's say we reduce our forms to a Gauss-Jordan reduced form matrix. That's what this would be. We have a unique solution when we have a full matrix, no zero rows. When we have a unique solution, it's very, very straightforward and simple to write this out. We literally just do x1 equals minus 3, x2 equals 4, and x3 equals minus 2. So x1, x2, x3. Okay. You can see that by putting it back into original system of equations. If we do that, it should also be very clear. It is also possible to have no solution, and that's when we end up with a false type of a statement. And that's where we have a row of zeros, but it's not all zeros. The augmented part is non-zero. This says no solution. There is one other type of form, and I'll go into this one a little bit more because this is infinite solutions. And that is when we have a row of zeros. However, it's also zero in the last point. Knowing previously, this is an infinite solution type of a result. When we have this, I'm going to turn off my video. One moment. When we have this type of a solution, does that help? Not much. So when we have this type of a solution, 1, 0, 0, 0, 1, 0, 1, 2, 0, augmented, minus 3, 4, and 0. We start with x3, and we say x3 equals an arbitrary value. Generally speaking, we choose that arbitrary value to be t. So x3 equals t. Then we look at what does x2 equal? Well, x2 plus 2x3 equals 4. Okay. Plugging in t, we have x2 plus 2t equals 4. So x2 equals 4 minus 2t. Okay. And then we do the same thing for x1. So we have x1 plus x3 equals minus 3. x1 plus t equals minus 3. So x1 equals minus 3 minus t. Now when we write the solutions, generally we're going to write them in this form. x1 equals minus 3 minus t. x2 equals 4 minus 2t. And x3 equals t. So that is the approach to getting the solution. If it is possible, if we need to, we can also, so for example, if we had, if this second column, it is possible that we might let x3 equals t and x2 equals s, but that's only in the situation where we have, let's say, 1, 0, 0, 1, 2, 0, 0, 0, 0, minus 3, 0, 0, as an example. In this case, we would say that x3 equals t, just like we did previously, and then we would say x2 equals s. Now we solve this for x1, so x1 plus x2 plus 2x3 equals minus 3 plus s plus 2t equals minus 3. So x1 equals minus 3 minus s minus 2t. So our solutions for this one, this set of this matrix would be minus 3 minus s minus 2t, s, and t. Now, the algorithm itself for Gauss-Jordan is very, very straightforward to get consistent results. But it's very easy to make mistakes when you're doing this. Very easy to make very simple mistakes. So be cautious about keeping track of the signs especially. And as I noted above, it's a very good idea to use this method of noting what operations you're doing. Get your own method of doing it. Be very consistent about it. Do it regularly. Don't lose track of signs, and keep things in fraction form. Don't convert to decimal form. Keep them in fraction form. It's a whole lot easier. Be patient and practice. The more you do it, the easier it will get. If you choose the best pivots, you'll get results faster perhaps, and sometimes the math will be a little bit easier. But regardless of your pivot choices, you should get the same solution. That ends lecture number 3.